So, we're going to be talking about the XDC and how to implement it, plus a couple other cool little VHDL tricks. Now let's go up here and look at the different files that we have here. These are your design sources right here, and this is my design source, my main source. It's called Flowmeter, and under this we have many different components to this system. This is considered the entity, and these are considered components. And so let's see here. Let's look through what we have, and we'll start talking about how they communicate with each other to make the system work. I guess the first thing we'll do is we'll talk about the constraints file right here. When adding a constraints file, you would right click and say add source. Or maybe if it wasn't already added, it would say add constraints, but I believe you would be able to click on this, and then under this right here, under it, when you submit a constraint file to this whole setup, I believe you don't click anywhere in here, and it will ask you what do you want to add, and you could say add or create constraints, and then you say next, and it will see I already have one loaded in here, but if I hadn't, I could say add file and go in and find the file. Now I've included this file in the instructable. It's called master XDC. It's called the master XDC file. So you would go to that area and add the constraints file. Now let's talk about what the constraints file does. See, ours is called Basis 3 Master XDC. And what this does is here it is right here, is it allows for, it's all the very specific coding for this board, and pre-typed out names for the different switches or LEDs or interface devices that you may have on the board. For us, we are using, we need a clock signal, so we've enabled the onboard clock. And the way you enable something or disable it is by using hashes. So if you put a hash before it, it'll disable it, or if you put a hash, 2 hashes means that it's a reference, meaning it's never supposed to be unhashed. It will it means that it's only a reference. So like if we were using any of the switches, I would uncomment this, and you can see the color changes right here, and we would, this file's been changed in the past, so otherwise these would probably say something like SV0 or something, and SV1. But basically so that would be like if you were using switches. So basically you reference whatever name you put in these brackets here is the same name you're going to use in your VHDL code. When we get to that, it's over here, and that's how you will make your hardware, be able to talk to the outside world, so to speak, with LEDs, switches, or some kind of using the ADC or other options that the board has for digital I/O. So here is where we've implemented the bar graph, if you will. I'm actually only using half of these, so you could enable all of them, and the way to enable all of them at once is to select them all and come over here and hit this to disable them or not. I don't know what IDE you may be using. You might not have the option to comment or uncomment an entire section of code, but in Vivado you have the option to do that. So I just went in and said I'm going to use all these lights right here, which I only ended up using half of them because for some reason the range from 8 to 15 I was having trouble getting those to operate for some unknown error that I didn't understand. But anyways, you want to, these will be commented, uncommented, I believe, already in the file that you will download. If not, you can go through and go to the LED section and just uncomment all these down to here. The next segment is for the 7-segment display, which is the red readout, and this has 6, I believe, maybe 6 or 4 and 3, 7 individual segments plus a decimal point down here, and those have been those are written like this. This will, in the stock file, which you don't have, but in the stock file these will say DP instead of seg0, just something to be aware of in the future for future projects if you download a stock file for this. And then last but not least, one of the more important things is the actual pins that you'll be using that connect to the ADC. And those are here. And here's what I've labeled them. So I've changed the names of these to ADC1 and ADC0. Those are the 2 pins you'll see on the board have a green and black wire stacked on top of each other, black on the bottom, green on top. And this is your positive and negative, meaning the difference between 0 being one between 0 and 1, which is oh, I can't seem to find the words right now. Anywho, I'll explain further in when you start digging through the code and why everything works, or at least the electrical side of it. Okay, so that's pretty much it as far as the things that you're going to be modifying just to get the ADC operational. So that's the master XDC. In this file, you'll notice the heading is up here, and it's going to stay up here, even if we go and open up another file. So this is my main, so to speak, my main file here. This is my entity, and this is where we will define what goes into the entity. And there's chunks of code that we will be going through and talking about what happens here. So first things first, I'll expand this and be able to point out the individual items to you. For our setup for this tutorial, I have named an ADC, which is a 2-bit signal that's going to be coming in from our pins off the board, and that's well, you could say 2 bits. It's actually going to be an analog signal, and so not really bits, but this specifies how many lines we're using, which is 2. And we'll be looking at the difference between them. So 0 being 1 and 1 being 2, if you will. two separate lines. Then we have a clock. This is also an input. And as you can see, we only really have two inputs. We need a clock and we need that analog signal input. And what we're going to do with that is we are going to use the segments and the anodes to display, to give a readout, and then the LEDs to give a more visual representation on a bar graph. So the LEDs, they've been initialized here with this bit of code. Not too sure if you have to do this. I just did it because I was having issues, and I thought that it might help, and it's been in there. It'll probably work without this. Nonetheless, if you know anything about VHDL, you don't want to have a semicolon at the end of this before your ending quotations or parentheses. So, I hope I'm not rambling too much. Bear with me. So this is your this is everything that defines the inputs and outputs of your actual the functional end product. And then we go in and we have to define different blocks of code that this system uses in order to operate. The most frustrating and daunting of all is going to be this right here, which is the XADC, which stands for Xilinx Analog to Digital Converter. This is an IP, meaning an intellectual property, and you can't modify how all this works in the background, but you can modify all of this up front, meaning you could change all different kinds of settings and how many things you're looking at when you want to look at them, and so forth. So we're going to get back to that. I'm going to just start pointing stuff out. So this basically looks at two pins on the board and finds the difference, a difference between 0 and 1 volt. And it looks at the difference between the two pins. One needs to be referenced to ground, and the other one will be referenced to 1 volt and vary. What this does is it looks at that pair and looks at the difference between them. And if there is no difference between the two pins, if they're both grounded, that means that will give out a 12-bit signal, which in our case has been crunched down to 8 bits. We're only using 8 bits of it. So it'll turn into an 8-bit signal from 0 to 255. So it'll have 256 individual steps that it can fill with that value. So with that being said, it will give an 8-bit output from this. So this looks at two pins and gives you an 8-bit signal from 0 to 255 based on the difference in those two wires. So that's a component of our entity, our main entity here. Another component of our main entity is the 7-segment display. And I didn't actually write this, but I was taught how it works and what to feed it, and so this has been provided as a file in the tutorial. Basically, it has an input here, so ALU value, and this will be 7 bits, 0 or 7 down to 0, so 0, 1, 2, 3, 4, 5, 6, 7, which is 8 individual bits, and this it looks at this signal, which initially I just had piped. I had piped the ADC directly into this, and it was working. However, there was an aliasing problem because of how fast it was switching. It was blurring the output, and you couldn't quite tell exactly what your value was. So that was slowed down. Instead of this looking directly at the 8 bits from here, I sent the 8 bits into something that would slow down the signal. So this is going really fast. I sent it into a bunch of flip-flops, which are right here. I called it 8-bit data pass delay. So the 8 bits will come in here, and then so that's the fast input, because that signal's coming in and it's changing rapidly, and that's what was causing the aliasing between these two. So instead of piping this directly into here, I piped all this, or the 8 bits from this, into here and slowed it down. So the 8 bits came in, and it would only update periodically, and I don't know exactly what the step is on that update, but it's I think it's close to a quarter of a second. At least that's what it looks like from looking at it. And so this only updates every quarter of a second, which gets rid of the blurry, the aliasing that was being caused by too fast of an input. If you look at 7-segment displays with multiple digits and understand how they work, you'll understand why I was getting aliasing, but that's a little further than I can go in this video tutorial. So anyways, you have the 8 bits that come from the ADC. They go into my little guy here to slow him down. And also, those same 8 bits are also being looked at by this 8-bit bar meter here. Okay, and the way this works is it's pretty simple. The 8 bits come in, and those, based on whatever value those 8 bits are, for me it was, we separated them into, I believe, 64 bits each. So we took in a signal that was 256 bits wide and said, okay, every 64 bits, we're going to turn on one LED. So we have 8 LEDs total on the board, and so every 64 bits we have an additional LED turning on. And so that's what this code does here. So we have a visual bar representation of what's going on, of our value, so to speak. And then this right here is the clock divider, and I used this right here. Takes and slows down the flip-flops in the bar meter, or not in the bar meter, in the data pass delay. So this is what's giving, this is only cycling once every 4 seconds, or once every quarter of a second, it seems. So it's slowed this down a lot, and it's gotten rid of the aliasing. And that's our update now is what I called it. And so that is being, that's getting this clock right here. I think S stands for slow clocking. This is, so this device here takes the clock signal input and then divides it down and makes an output. It gives you a slower output. And let's see, what other items do we have here? Yep, and that seems to be everything. So real quick, ADC looks at 2 external pins, measures the difference, and that outputs an 8-bit signal that is referenced or looked at by 2 different components. One of those components being the 8-bit bar data delay, or 8-bit data pass delay, and an 8-bit bar meter. and the bar meter reads out on the LEDs, and the data pass delay then feeds the 8 bits that update less quick into our 7-segment display to give us a nice, clean, readable readout. And the delay is controlled by this clock, which has been slowed down. So these are all, you can see these are all components. These are called components. And that's the last component. So this totals 1, 2, 3, 4, 5 components. And then the main entity, which includes all these. So the architecture behavioral of our flow meter, meaning what is there that makes this, is all right here. So these are our outputs, here, here, and here. And those all get signals from this and this. Okay, so bar meter and our 7-segment display. Now let's get into all of this down here. So this is where we implement our individual components. So first things first, we have the clock right here, and can think of this as piping. We basically take and pipe the signal, which this clock divider is getting a, it has 2 things that I need to take care of, this and this, and I need to make these 2 items look at inputs from the board and give outputs back to some part of the board or some logic in here. So this is getting clock, and this clock right here, CLK, is it automatically knows if we're referencing to it. If it's not a signal, and I'll explain what signals are in a second, it's coming from our entity, and sure enough right here we have that called CLK. So it comes from there, and so it has been piped. I call it piping, but I know that's probably not a good term. Probably don't use that. But it's been piped to our clock. It's been connected to our clock here. And the slower clock has been piped or connected to a signal path, meaning just more pipe, that we called slow clock. Okay, so this is a signal, and you have to specify what kind of logic it is. So if you know VH, I won't go and get into that, but we use a signal here, and I've called it slow clock, and we've piped it into there. And what happens is you take that now signal and you bring it down here to our 8-bit data pass delay, and so this 8-bit data pass delay needs that input for update now, so it's going to get that through this signal. Because you can't just say that update now gets SLK because this portion of the code doesn't recognize another component out of the code. This component doesn't recognize, this component doesn't recognize other components out of the code. It only recognizes signals that you designate or the main entity itself, which is up here. So let's go back down. So there's a lot of that going on, different signals being piped to different areas, so different connections, and you'll see a lot of that going on. And so So I've labeled my signals here. ADC interconnect or intcon. Interconnect is another word for signal, if you will. Signal, so this is ADC slow intcon. I believe I ended up not using that, so it's just kind of hanging out. Or wait, no, maybe I did. Yeah, I did here. Oh, yes, that is my that's my slow normal. That's my slowed down signal. So it has been that's the analog to digital conversion that's been slowed down, and that has come from here, which I've called held sample, because it's a sample that's being held until the update now says to change it, and that is being sampled by this. So got to get into the meat and potatoes of this here in a second. That is, I think you may be getting the point of how signals interconnect these items and how that works. So let's go up and look at this right here. This was the hardest part to all of this, is knowing what to put here, where to pipe all of this, how to connect all of this stuff. And a couple of the most important things is the address of the pins that you're using. So I ended up using, let me see, I think it was pins 2 and 16. Well, you could see on the board, if you're looking at the actual X or JX80C, it's the second pin set from the right. And this turned out to be the address for it. You could find that information in the manuals that are provided. Or just use it here and use the same pin set and you'll be fine. So, let's see here. Did I end up using... yes. And I set it to 1 instead of just specifying it's 1. So, in order to enable the device, we've given it a 1. So on. 1s mean on and 0s mean off. Next, we'll talk about the input data bus. Which we've set to 0, all of it to 0, others to 0. You'll have to follow this kind of blindly, because even some of this I don't understand entirely how it works. But this code works in VHDL. The write enable we're not using, so it's going to be set to 0, single quotations. The data out, this is the most important right here. This is a actually 16-bit signal, so 0 through 15. So it's on 2 separate lines because we're breaking it up. We're going to use 15 down to 8 as our output bus, and so that's 8 bits of data right there that we need to use. We've used the most significant bits because those are going to be the ones that that we need to change for a larger step range. So we're using those, and we are not using the least significant bits from the least 8 significant bits. So this has been just connected to a signal and kind of left alone up here. it's not quite the way you should do things, but I believe I was having trouble trying to get some other stuff to work, so that got left that way, and it works. So these are leftover output data bus, not used. So data ready out. So this would normally send a signal to something and say, hey, data's ready to read, go ahead and look at it. I found that just setting this to open was easier. This is the clock signal here, and you just feed it the clock, and it'll do its work. So you want to feed it the full speed clock, and it'll hum. We have the reset signal. We're not resetting ever. Wasn't any need for this simple project, so that's just set to 0. These right here need to be piped to your pins. My pins are ADC 0 and ADC 1. So it looks for a difference between these two, and as you can see, the P in the N here and here designates positive and negative. And so if you go up here, we can see this ADC right here, and it's 2 bits. Okay, it's a vector, so multiple, 2 bits. Anyways, let's go back down. Let's see, that was these. So busy out, and just send it to open. This would be like if you needed some information and you wanted to sample that signal, and you looked at this signal and it was connected and it said 0, then or 1, that means, hey, I'm busy, wait a little bit longer, then ask again for the information. So we just set that to open because we're not using it. Channel out, this selects multiple channels, we're not using it, so set it to open. EOC out, end of conversion signal. This gets sent to enable int. Oh, that's right, I was wrong. DIN in, so this needs to be sent to this in order to work properly, otherwise it doesn't turn on. So in order to pipe this to itself, we needed to use a signal, which was here. We initialized it to 1 to start working. Okay. End of sequence signal needs to go to open for what we're doing. Alarm, open. We're not using any alarms, and these get 0s. We're not using these either, so there's no reference to those. Okay, so I think I'm going to end this video here, and then I'll start making some shorter videos talking about how the individual components work and how to implement them, or how to write them and whatnot. So let's go ahead and end, and we'll come back in another video.